In this video, we're going to discuss the hydration of an alkene. So we've seen this reaction in reverse when we started looking at how to make alkenes. And this reaction is in equilibrium, so we can push it one way or the other. So to think about how to do this, we're going to recall Le Chatelier's principle. Which is that a system at equilibrium adjusts to minimize stress. So one of the ways that I can impact the equilibrium of a system is to add a product or remove a product, add a reactant or remove a reactant, and that addition or removal can shift the equilibrium one way or the other. So I can shift towards products or shift towards reactants. So I'm just going to write as a note here, a shorthand note, minimize stress. I'm going to say by shifting. So if I want to go to the alcohol side, then I would add water to go to the alcohol side. If I want to go to the alkene side, then I would remove water. So we can add or remove water in order to push the equilibrium one direction or another. If we want to go towards hydration, so adding water across a double bond, we're going to have excess H2O in order to push the reaction towards the alcohol product. So if we add H2O, we shift towards products, and my products are the alcohol, as I had written the equation there. And if we remove H2O, we would shift towards reactants. And the reactants would be my alkene. So we can use that principle to drive the reaction in one direction or another. This reaction, regardless of which direction we're going, is often acid catalyzed. And the difference is whether I have dilute acid and a lot of water, which would make it go towards the alcohol side, and if I have concentrated acid with not much water, and I could even remove water as the reaction went along, and that would make it go towards the alkene side. So let's look at a mechanism here. If we're going to do hydration, we're starting with the alkene and adding water. So let's start with this alkene, and we're going to add H2SO4 and water. What you might also see is H2SO4 dilute, just meaning it's an aqueous solution that's been diluted down. Now the product of this reaction is going to be a Markovnikov addition of water. So you're going to see the alcohol on the more substituted side, and that has to do with the mechanism, which we'll do on the next slide. So in my first step, those pi electrons that are above and below the plane of the molecule and more accessible are going to interact with that H+, the acidic environment that we have. And that is going to protonate my alkene to give me an alkane carbocation. So what happens here is I have two choices. The H is going to go to the less substituted carbon so that the more stable carbocation intermediate is formed. So here I have a tertiary carbocation. Once that tertiary carbocation is formed, or whichever one is most stable, that water is going to act as a nucleophile and attack that tertiary carbocation. I'll go down here. And now I'm almost at the point where I have my product. I just need to deprotonate. The best base that I have in solution is going to be water. I'm in an acidic solution, remember, so I won't have any strong bases in this solution. So another water molecule can come along and deprotonate that guy. giving me my alcohol with a Markovnikov addition. So the hydration of alkenes is an acid-catalyzed aqueous environment that gives a Markovnikov addition of the alcohol. This happens because the most stable carbocation intermediate is formed. In this case, the choice would have been secondary or tertiary. The more substituted the carbocation intermediate, the more stable. There was no option for a resonance stabilized carbocation intermediate, so tertiary was as good as it gets. Then you have water acting as a nucleophile. You've got your carbocation electrophile intermediate. Those will combine, the water will be deprotonated, and you'll end up with your alcohol.